So yeah, so finishing up topic 5 today and then having our quiz on Friday. And then IAs, if you're still in the middle of working on your prep or your background research stuff, if you're still kind of trying to figure out what you want to do, definitely keep working on that because that you can do. But as far as anything after sort of background research, we can't do yet because you guys can't come into the building and get into my room to do anything with chemicals. So for right now, that part of the IAs is on hold until we won't be able to come in until sometime after spring break, probably. So all the dates are going to kind of get pushed back. So for right now, for IA stuff, you just need to be working on, if you haven't developed an idea yet, you need to be looking at your idea and kind of doing that prep and the research stuff. And then once you're totally done with all the prep and all the background research and you're good to go with all your planning, that's where you'll basically stop for now because we won't be able to come in and collect data or do anything until after spring break. Okay. So this week we're finishing up topic 5. We're on 5.3. It's the very last section. And it was posted for you guys last week on Canvas to do, but we're going to go through it today just to clarify anything. And so it's on what we call bond enthalpies. So this is different from enthalpy of formation. Enthalpy of formation is what we had done, back before we started IAs. That was in 5.1 and 5.2. Okay. And so bond enthalpies actually deals with the enthalpy that's contained inside of a chemical bond. And so what we need to kind of understand or know, take away from this is if you form a bond, you release energy. Okay. A lot of people think it's the opposite. A lot of people think that when you form a bond, you should be needing energy because you're putting energy into the bond, and that's not true. Okay. Bond breaking actually requires energy. So if I have, two atoms that are bonded and I want to break them apart, I have to put in enough energy in order to overcome the energy that's holding that bond together. If I don't have enough energy to overcome that, then it's not going to break the bond. So it requires energy to break a bond, which means that bond breaking is endothermic. Sorry, I started to spell it wrong there. And so bond breaking requires energy, so we call that endothermic. But when you form a bond, you're putting them together. They're becoming more stable. And so yes, there's going to be some energy in that bond, but whatever energy is not used to form the bond, that extra energy is what is released. And so because there's energy released when you form a bond, that is going to be exothermic. And so that's kind of a key thing that they like to ask is bond breaking endothermic or exothermic? And so make sure that you kind of have those all kind of lined up, that you know that bond forming releases energy, which is exothermic. Bond breaking requires energy, which is endothermic. Okay. And then kind of the definition that they use on here is this average bond enthalpy. An average bond enthalpy is the energy needed to break 1 mole of a bond in a gaseous molecule, and it's averaged over similar compounds. So you need to know that definition because that's one of those key definitions they may ask you about, and it needs to be specific. Like you need to mention that it's the energy needed to break 1 mole of a bond, and it's in a gaseous molecule. It has to specifically have that 1 mole and the gaseous molecule. And it also has to have this part about averaged over similar compounds. The reason this is important is because when we calculated enthalpy of formation earlier in 5.1 and 5.2, those are specific to that molecule or to that substance, okay? Bond enthalpies, because it's an average over similar compounds, they're not as precise. And so sometimes if you use bond enthalpies to calculate the enthalpy change for a reaction, and you compare it to what you would get if you use the enthalpies of formation, which is what we were doing before, the answers will not be exactly the same. And so enthalpy of formation is actually the better one to do because it is not averaged over other compounds. And so sometimes they will ask you, they'll tell you to solve it both ways, and they'll ask you, why are they different? And your answer would be something to the notion of the fact that the bond enthalpies are averages over similar compounds. And so they are not as exact. They're not as precise as the enthalpies of formation. Okay. So what we're going to look at today is we're going to talk about how to calculate enthalpy change from known bond enthalpy values. There's a chart in your data table that, or your data booklet, that we'll use for that. And then comparison to experimentally measured values. So like I said, they'll have you calculate enthalpy change using the bond enthalpy values, and then they'll have you compare it to either something that's been experimentally measured, or maybe they'll have you calculate it from enthalpy of formation values, and they'll have you compare it to that. Sketching potential energy profiles, determining whether the reactants and products are more stable. That kind of goes back to what we did in 5.1, where if the reactants are lower than the products, their products are going to be more stable, and it would be exothermic because heat was released. And if the products are higher than the reactants, that means that the products are less stable, and that's endothermic because it absorbed energy. And then specifically, we're going to relate this bond enthalpy to a couple of molecules, to the oxygen molecule O2 and to ozone, which is O3. And we're going to talk about how that relates to some environmental issues with like the ozone layer and UV rays and like harmful things that are in the atmosphere. So as I said, bond enthalpy values, they're in section 11 on the data booklet. And so if you need to look them up to do any kind of calculation, that's where you would look them up on your data booklet that you have linked here on Canvas. And then notice this last bullet. This is kind of what I was talking about. Average bond enthalpies, they're only valid for gases and for calculations involving they might be inaccurate because they don't take into account intermolecular forces. And so intermolecular forces are something that we'll cover in topic 4 when we do that. But intermolecular forces are forces that hold different molecules together. So, when water is a liquid, it has intermolecular forces that hold the water molecules close to each other. But when you boil it and turn it into water vapor, you break those intermolecular forces, and because the molecules are spreading apart. And so average bond enthalpies are averaged over similar compounds, and they don't take into account these intermolecular forces. And that's why they're not always very accurate. All right, so for bond enthalpies, we already kind of talked about the definition. Energy needed to break 1 mole of bonds in a gaseous molecule, and it's averaged over similar compounds. We talked about this, bond breaking, endothermic because it requires energy, bond making, exothermic because it releases energy. Here's the equation that you use when you're calculating the change in enthalpy based on bond enthalpies. You add together, so this symbol is sigma. Sigma means the sum of, so that means you're going to be adding together a bunch of numbers. So you're going to add together all of the enthalpy of the bonds that are broken, and bonds that are broken are going to come from the reactants, because the reactants are the ones that we're going to have to break the bonds. Okay. And then you subtract all the sum of all of the bonds formed, and the bonds that are forming are going to be the products. So this one is different from using the enthalpies of formation, because when you use enthalpies of formation, like we did earlier in this topic, you always do products minus reactants. We added up the enthalpies of formations for all the products, and then we added up all the enthalpies of formation from the reactants, and we did products minus reactants. So when you're asked to calculate this using bond enthalpies, it's reversed. And it's because of this equation right here. We have to do bonds broken minus bonds formed. And so, all right. So as I was saying, this is the opposite. So you always do reactants minus products on this one. So be careful, because from now on, if you're asked to calculate based on enthalpies of formation, it's products minus reactants. If you're asked to calculate using average bond enthalpies, it's reactants minus products. And a lot of times people will mix them up once we've covered both of them. So you just want to be very careful when you're reading your questions and look at which one do they want you to use. Bond enthalpy is this way. Enthalpies of formation are the way that we had done before. So what you would do, this is an example. So here's a chemical reaction. This is the combustion of methane. So we have methane, which is CH4. It's being combusted, which means it's being reacted with oxygen. And it makes carbon dioxide and water. Okay, those are always the products of a combustion reaction. And so what you need to do is you have to draw out the Lewis structures for these compounds, because you have to know how many bonds and what kinds of bonds are in these molecules. So sometimes they will make it easy and they will give them all drawn out, like on this example. Sometimes they won't. And so what I would advise is common compounds, like, you know, like oxygen, O2, and carbon dioxide, CO2, and water, H2O. Those are pretty common molecules. You're going to see them pop up a lot in reactions. And there are a few others that are going to pop up a lot. But what I would like advise is to sort of kind of memorize what do these look like, okay, and how to draw them, because they're very common. They're going to pop up a lot. So if you see O2, that's the oxygen molecule, and that's always two oxygens double bonded to each other. Okay, so there's one double bond oxygen there. For carbon dioxide, for CO2, it's always going to have the carbon in the center, and then the carbon is going to be double bonded to each oxygen. And so in this one, there is a carbon oxygen double bond here, and then there's another carbon oxygen double bond here. So carbon dioxide always has two carbon oxygen double bonds, okay? And then for water, for H2O, oxygen's always in the center, and it's single bonded to each hydrogen. So that means that in a water molecule, I have a single bonded oxygen hydrogen, and I have another single bonded oxygen hydrogen. So there are two single bonded OH bonds in a water molecule. Now notice on this, there are two oxygens drawn and there are two waters drawn. Why do you think that is? Any idea, any guess for why?
Because of the two in front of them?
Exactly, yeah, because they both have two coefficients. So remember that, you have to take that into account when you're drawing the structures out. So if it has a 3, you got to draw 3 of that Lewis structure. If it has a 4, you're going to have 4 of them, because that's going to impact your numbers, and that is going to affect the answer that you get. So just make sure you're paying attention to that. Okay, so that being said, once you have everything drawn out correctly, then this is where you would go to your data booklet for table 11. Unless they give you a table in the question, sometimes they might give you a reference table in the question to use the values, but if they don't, they're probably going to tell you to use, or they're going to assume you know to use table 11 in the data tape booklet, okay? So what I would say is, I would say before you go look at the data booklet, let's write out what we have here. So in this molecule, I have CH single bonded, and there are 4 of them. Okay, they're all the same. They're all C bond single bonded to an H. So I'm going to put, okay, I have 4 CH bonds, and they're single bonded. Then I have 2 oxygen double bonds here. And then, and that's the reactant side. So I'm going to kind of put a line here just so I can see I'm separating my reactants and products. And so now over here on the product side, I'm going to switch colors. So I have here, there are 2 carbon oxygen double bonds. And then in the water, each water has 2 OH singles, and there are 2 water molecules. So that means altogether there are 4 OH single bonds over here. And so now I need to look up these 4 bonds on the table 11, or the chart 11. So I need to find CH single, OO double, CO double, and OH single. So I'm going to switch over to the data booklet so we'll go down to table 11. So that's 10. Okay, here is table 11. So notice it's labeled bond enthalpies and average bond enthalpies at 298 Kelvin, okay? And so the way that this is set up is this chart, these are all for single bonds. So I need to find my 2 elements and kind of go to where they intersect. So our first one was CH. And so it doesn't really, you can go either direction. So I can go C here, H here, and then here is the number, okay, for that one. Or I could go C here, H here, and look, it's still the same number. So it doesn't really matter which order you do the elements in, you're going to get the same number. So CH is 414. So let me go back to our notes. We're going to write this one down. So CH is 414, but that 414 is going to get multiplied by 4, okay, because I have 4 of those CH bonds. So then I'm going to have 2 times whatever I get for OO, but you got to be careful because this one is a double bond. And so this chart is just for single bonds. Okay, so I don't want to look for the oxygens on this chart. What I want to do is I'm going to scroll down here. There's a list down here that have a few multiple bonds. And so if you have something that's a double or a triple bond, I want to look down here. And here is the OO double bond right here. Okay, it is 498. So I'm going to go back over here and write down 498. And so that's my reactant side. So 4 times 414, 2 times 498, and then I would add that together, okay, for the total. For the product side, now I need to look up CO double bond. So we're going to go over here. So CO, and this is a multiple bond, so I want to look down here. So here's the CO double bond. It's 804 kilojoules. So I'm going to go back and write that one down on my notes. So 2 times 804. And then I need to look up OH. Now this one's a single bond, so I'm just going to use the chart at the top for this one. So looking up here, OH, here is O and here is H. So right here, it's 463. Okay. So we're going to go back and write that one in our notes. And so now I have all my numbers. So now what I need to do is I need to multiply and add together this reactant side. I'm going to multiply and add together the product side, and then I'm going to subtract reactants minus products. Okay. So I haven't done this one yet, so let me put it in my calculator. 414 times 4. So this one is 1,656 plus 996. So total over here, we have 2,652 kilojoules per mole. And then on the product side, we have, let's see, 804 times 2. So this is 1,608 plus 1,852. And the total is 3,460 kilojoules per mole. And so then I need to subtract these. My last step is subtract reactants minus products. So 2,652 minus 3,460. And my answer is negative 808 kilojoules per mole. Okay. And so this would be an exothermic reaction because my answer came out negative. So that means that this whole reaction is exothermic based on that number. Okay. So that's basically the process that you would do. The only thing that will be different is obviously you're not always going to have the same bonds. And so you'll have to use that data booklet to look up whatever bonds are in your problem that you're working on. But the basic process of, totaling up, multiplying and adding up all the reactant bonds, multiplying and adding up all the product bonds, and then subtracting the difference, reactants minus products, that is the same. And so there are a lot of just exercises on here, questions about what we talked about. And then there are some practice problems here where they've drawn out the structures for the more complicated things. Like, for example, here, this one is this structure. This one is this structure. Okay. They did not draw out H2 because that's a simple one. So that's kind of like the O2. So hydrogen, H2, it's just H single bonded to H because a hydrogen can't do double or triple bonds. Okay. So simple molecules, you're going to be expected to know how to draw those out, which you should have learned basics of that last year in 10th grade chemistry or when you took 10th grade chemistry before. But complicated structures like these other ones, they'll usually give them to you. Okay. So the last little bit today is just how does this kind of apply outside of chemistry? And so one thing that has to do with bonds and bond breaking and bond forming is ozone in the atmosphere. And so normally, sunlight comes to the earth, right? We have all these layers above the earth, the troposphere, stratosphere, all these other areas. And the ozone layer is this area here that's in blue on the picture. And what happens is the UV rays from the sun, the rays from the sun, there's different wavelengths. So most of the sunlight is visible light that we can actually see. And then there are UV rays, and the UV rays are the ones that are harmful. Those are the ones that's where they tell people to like make sure you like put on sunscreen so you don't get skin cancer, because the UV rays can mutate your cells. And then there's also a little bit of infrared, but infrared's not dangerous. So what happens is there's different kinds of UV radiation. There's A, B, and C. And so the ozone absorbs UV radiation that's in this range of wavelengths. And that's the ones with higher energy, like UVB and UVC, which can cause living tissue to be damaged, like cancer. Here's how this relates to our bond enthalpy. Up in the atmosphere, oxygen molecules, they can dissociate if they're in the presence of high energy UV radiation. When they dissociate, they form what we call oxygen free radicals. Free radicals are atoms that have a single electron, okay? And they're not very stable. We don't like them. Free radicals are bad. Everybody wants to have pairs of electrons, not single electrons. So then what happens is one of these free radicals, it can come and it can pair up with another oxygen molecule and it can make ozone. Ozone is O3. And ozone is what's dangerous. Well, it's not dangerous. Some ozone is good. That's why we have the ozone layer, okay? But what happens is ozone can be destroyed, okay? This next part talks about the destruction of ozone. It can dissociate in the presence of low energy UV radiation. So when you have ozone, if it comes in contact with low energy UV radiation, it can dissociate it back into that oxygen molecule and one of these oxygen free radicals. And then what happens is then that radical, it can go and it can react with another ozone molecule and it can make two molecules of oxygen. And so what happens is the strength in their bonds is what kind of plays into how they can be destroyed. In ozone, the bonds are intermediate because each one of them is like 1.5. Whereas in oxygen, it's a double bond, it's two bonds. And so this one's 1.5, this one's 2. And so the 2 is stronger. So oxygen has a stronger bond because it's a double bond. It requires more energy. So double bond, it's stronger, it requires more energy. And so it's broken with a shorter wavelength, because shorter wavelength means higher energy. Okay. For ozone, it can be broken with a longer wavelength because it requires lower energy. And so what happens is when you have those different types of UV radiation coming in, you can actually destroy the ozone, and that destroys the ozone layer, which starts to let in more of the UV radiation that is dangerous to us and to the environment. And so that's kind of how this whole thing kind of relates and plays into that. So kind of what you need to know is kind of which molecule, oxygen and ozone, like what's their bond order, and then what kind of energy can break their bonds. So is it high or low energy? And does that correspond to a shorter or a longer wavelength? Okay. And that is it for today. That is the end. So I'm going to